Okay, so in terms of attempts to actually do this on real data, so far, well, there have been two attempts, one by Kendrick Smith and one by Chris Harter and co. And they use WMAP data, but the WMAP data is just not a good enough resolution or sensitivity to be able to do a completely internal detection of the lensing power in the reconstruction. So instead, what they did was use these reconstruction techniques to make a very noisy reconstruction of the deflection field and then correlated it with a tracer of large-scale structure. So Kendrick used the NVSS survey, Harata and co used SDSS and NVSS. This is just a plot from Kendrick's paper, and the purple line, dashed magenta line here is the signal they're trying to detect. So this is the cross-correlation between the lensing and the galaxies. And the error bars here are the results of their analysis. And they claim sort of 3.4 sigma detection by doing this. So while you're in the sort of limit of very noisy data, then this is the best way to try and search for the signal because your reconstruction is very noisy. But for Planck, the noise is good enough on the reconstruction that we'll be able to do a fully internal detection. So you make the reconstruction using the lens CMB itself, and then you correlate it with the reconstruction. So the power spectrum for that should be the lensing deflection field. It's this thing here, and then the error boxes here, forecast from a long time ago by Wei Hu. The light boxes here are what we should be able to get from Planck, as opposed to an ideal experiment, which would have full polarization capability and high sensitivity. So what you can see is a very high significance detection is possible. And in principle, you can start to distinguish different cosmological models here. So the red line is a model, a different dark energy model, but with the same angular diameter distance to last scattering. So it will be degenerate in the effect on the primary CMB, but you can easily distinguish it with this lensing reconstruction. Okay, so the sort of parameters that really benefit from lensing reconstruction are those which are degenerate in the primary anisotropes. So in particular, light neutrino masses. So if any mass eigenstate has a mass less than about half an EV, then it's relativistic at recombination, and it has essentially no effect on the pre-recombination physics. They just look exactly like massless neutrinos. So their only effect on the micro background power spectrum then is via the late time integrated Sachs-Wolf effect. And if you have a simple sort of 6-parameter lambda CDM model, then you do actually get some constraining power from the integrated Sachs-Wolf effect. And you can sort of constrain at 68% the neutrino mass. This is taking just a single massive species at the sort of 0.2 level. But as soon as you fold in more parameters, so a more complicated dark energy model, for example, and other relativistic degrees of freedom, your parameter constraints degrade significantly because of degeneracies, and you just end up with asymptoting to this value about 0.5 eV, which you would expect based on these arguments about neutrinos being relativistic at recombination. So that's without using lensing information, but when you bring in the lensing information from the reconstruction with the CMB, you get basically robust constraints that don't degrade as you add in more parameters. And they're at a sort of interesting level, so the sort of 0.1 electron volt level. Okay, just a quick advert for the talk that's coming up next. So Anthony's going to talk about the bispectrum that is produced from gravitational lensing and the impact that this has on non-Gaussianity in the CMB. But given the time, I'll just skip over what I was going to review on that, because Anthony will cover it. And let me just end up by summarising. So Planck is working well. I'm afraid we've still got a few years to wait before the first cosmology papers will come out. But basically, we expect to achieve our main science goals. So the data look basically like we were expecting, and sensitivities are comparable to what were forecast pre-flight. The lens CMB power spectrum is well understood, and there are marginal detections of the lensing effect via this route. But to really get at all the information that is present in the lens CMB, you've actually got to try and reconstruct the lensing deflections themselves using this non-Gaussianity that is introduced in the lens CMB. We expect to be able to do this at high significance with Planck, and this allows you to break, in particular, this geometric degeneracy that affects the primary anisotropies. So we can expect tighter and less model-dependent constraints on dark parameters like the neutrino mass and the dark energy model. And one of the things we hope to do with Planck is just do a fully internal analysis of, for example, models with curvature, which, without using any prior information, but using the lensing reconstruction to provide the degeneracy breaking power. Anthony's going to talk about non-Gaussianity, so my final point then is just that there should be reconstructions coming up soon. ACT, SPT and Quad, I know we're all working away hard to try and do this, and obviously we'll hear what Planck will do in a couple of years' time. Thank you.
Very briefly mentioned the idea to study high redshift clusters. So two questions here. Roughly, where does the lensing efficiency peak? And second is, what signal to noise do you expect to get? Like from a single cluster, or you need to stack many to detect it?
So the signal to noise peaks. The redshift distribution, the source plane's at a redshift of 1,000, so it peaks at a redshift of about 2 with the lensing efficiency. It was actually Anthony's work who did this, so he can probably comment if he's here on the signal to noise. Are you here, Anthony?
It's very exciting to see the constraints and potential from the CMB. And just to reverse your comment on your last slide there, if there is primordial non-Gaussianity, then how much do you worry about primordial non-Gaussianity messing up our ability to measure lens potential for the CMB?
Okay, but that way round it isn't too bad at all. People have looked at this, and at least for the sort of simple models they looked at, it wasn't really an issue. It's much more an issue going the other way, in that lensing can very easily mess up your inferences about primordial non-Gaussianity.